All right, take a look at this double integral right here. The good news is that we didn't have to set it up, because that's half the battle sometimes when you get one of these homework problems and you're the one who has to set up the double integral. So this is already set up for us. Okay. Now the answer is already shown, so I just wanted you to see that. So technically I shouldn't show you the answer, but so let's take a look at how would you do this. Well, as we talked about before, what you want to do is you want to make sure that you do the inner integral first. So the inner integral is with respect to x. So we're integrating sine 2x minus 5y with respect to x. So that would mean that you're going to hold y constant. You know, y gets treated like it's some number, any number. So you're going to use u sub with the sine rule. So the sine rule says the integral of sine of u du is equal to negative cos u, right? And I'm not going to put plus c for a reason, because look, when we do these iterated integrals, it's going to turn out that you're never going to get a plus c in there. Now, later on, we're going to have sort of a, you know, I'm going to give you the, I want to see sort of a plus c of y or something like that later. But these, you're always just going to get an actual pure number as your answer. So we are going to use u sub. And because we are going to use u sub, in order to receive full credit on my quizzes and exams, you always have to identify the u and the du, else you're going to lose points, even if your answer is correct. I do want to see it. So let's see if I can get back into, so u is equal to 2x minus 5y. And du, now remember, we're taking the derivative with respect to what variable?
X.
X. So it's just going to be a 2. You know, dx essentially. But I see a 10 in the integrand, which is fine. You can pull the 10 out. But when I put the 2 in, I'll divide out by the 2. So right now, the integral will now look like sine of u du, and we still have the outermost integral left. So I continue to write that. And then we're going to have the antiderivative, which is minus cos u. But be careful, I'm sort of doing intermediate steps here, because I'll back substitute what my u is, and it's the quantity 2x minus 5y, and the limits on that innermost integral look like they were going between y and, what was it again? Pi halves. Okay. So you guys should know your fundamental theorem of calculus says substitute the upper limit first, and you're going to substitute it into the x only because we just integrated with respect to x. So you have to go, okay, 2 times pi halves there minus the 5y, and then minus, and then you'll substitute that lower limit to negative cos x 2y minus 5y. Woo, this is one big hot mess. This whole thing eventually we'll do dy. Okay, so it's getting kind of messy, and that's how these get in the intermediate steps. So what do we have here? We have minus cos, and after reducing, this is going to be pi minus 5y for an argument. And then minus minus is a plus, so then we'll have cos of, and then, ooh, 2y minus 5y. Interesting. I believe that's going to be negative 3y. So we're going to integrate these two cosine terms and with respect to y. Now, at this point, folks, it is indeed a calculus 1 problem, but you have to be careful because you don't want to get too cocky. I could do this, blah, blah, blah. I still want to see you identifying the u and the du each and every time. And I know this sounds kind of strict, but you'll thank me later because it prevents some silly mistakes from happening. Just take a few extra microseconds. So you have two completely different cosines. So you're going to have two completely different u and du's. Maybe I should use different letters here, but I'm just going to use u for this guy as pi minus 5y. So the du is negative 5 dy. So he'll need a negative 5 in there. And then I'll kind of do this one separately. This u is negative 3y, so his du is negative 3. dy. So I still have this 5 that's, you know, all the way out there. So I'll sort of do this. And I'll do these separately. So the first integral, I'm going to divide by -1/5. And it looks like I'm going to have my negative cos u du for that first cosine, plus, and I'm going to need the -3, which means I'll put a -1/3 out in front there, and then I'll have a cos u du. Is everybody following me here?
Yeah.
Yeah. Nothing weird, right? Just
No.
Calc 1, you know, tedious, but doable, right? So the first integral of minus cos is going to be what? What's the integral of cos? Isn't it sine? So this is going to be a minus sine u. And then this one, I'm going to have sine u. Does that look like it's working there? I hope. Boy, let's hope this all works out. Oh, I forgot to, there we go. Get rid of that. Okay. So before you do any substituting, you got to be careful here. And I'm going to do a couple things at one time. I'm going to distribute this 5. So I'll have those 5s cancel. I'll have a minus minus. I'll have a plus sign of u. But the u for the first term was pi minus 5y. And then plus, or maybe I should say a minus 5/3. And this sine of u will be sine of -3y. That was a different u. But both of those guys have the same limits, and the limits on that outermost integral, if we look here, was 0 up to pi halves. Okay. So we're going to evaluate this mess between 0 and pi halves. Okay, fine. So what the heck are we going to get? Sine of pi minus 5 times pi halves there, minus 5/3 times sine of -3 pi halves. Okay, then you just use your trig stuff here. Yeah. And I think you can finish this one out. I'll just say et cetera, et cetera. I'll let you guys figure out the rest. But the hard part when you're doing double integrals is remembering, you know, not only your rules of integration, but what variable are you integrating with respect to at that moment. So you got to kind of keep it clean and keep it all together. So that can be a little bit tricky. And of course, you know, making silly mistakes with a negative is super common. But the good news is, you know, on your quizzes and exams, I'm pretty merciful about giving you partial credit when it comes to forgetting a negative or putting a negative in there when you're not really supposed to. So there you go. Any questions on this problem?
So the other side was just going to be 0, right?
But I'll let you finish it out. And
Okay.
then questions, we can talk about it after class. Or I have office hours today. So
Okay.
I want to move on. So I'm going to put you in breakout rooms, but I'm not going to put you in breakout rooms very long. You're going to hit it and hit it hard and hit it fast. So on example 5 here, I want you to look at this double integral with you and your buddy. And you have to do a couple things here, just like we did last time. You're going to sketch the region of integration because this is representing an area. How do I know this double integral is representing area? Does anybody remember from the last time what's the giveaway that this double integral is representing area between curves?
Because the integral of 1?
Yeah, the integrand is just a 1. That's how you know, boom, it's representing an area. So you're going to sketch and then shade in to get full credit the area that's being represented. And then afterwards, you and your buddy are going to evaluate the iterated integral, which isn't too hard. And then this is the hard part. Here's the challenge. You're going to switch the order of integration. And then you'll evaluate the new integral that you get after switching the order. And hopefully your answer is the same as part B. If not, oops. Okay. So turn your mics on so you can at least talk to each other. And get some. Now, you guys know that you can, when you're in a breakout room, you can go pull up a whiteboard together if you have a stylus, or even use your mouse cursor to write on a whiteboard. So if you don't know how to do that, look at your little dashboard Zoom controls and do a share screen and select whiteboard, and you can kind of have fun with that, and play around and write stuff down instead of just talking, because that can be a little bit tricky to talk math and then not be able to see somebody else's work. Okay. So let's do some breakout rooms here. Woohoo. All right, get ready. You're going to do some thinking here. All right. Good luck. Okay, guys, how'd we do?
Pretty good.
Yeah,
Yeah?
we did fine.
Was this beneficial to you, or you got a little bit of your kinks ironed out?
I think so.
Yeah.
All right, especially if you didn't get a chance to review last time, maybe it was helpful. So here's what I'm hoping, that when you look at this double integral, you use the techniques I went over last time to sketch your region. So let's start with the outermost integral. Since it has to do with y, write these down. Y equals 0, y equals 1. Write those equations down. and then graph them. So y equals 0 is a horizontal line living on top of the x-axis, and y equals 1 is another horizontal line intersecting the y-axis at 1. The innermost integrals limits, you write the equations for those down. Since the variable of integration is x, you have x equals cube root of y and x equals y squared. Now, x equals y squared, I think we all kind of know just off the top of our head, or at least we should. At any rate, it's a horizontal parabola. X equals cube root of y, I don't know, you know, and your graphing calculator only lets you graph functions of x, now, or you could parameterize this and graph the parametric equations. But a simpler way is to solve for y, and it'll be a little bit easier to graph. So if you cube both sides of the equation, you'll get y equals x cubed, which is a little easier to graph. Now, when you graph that, it ends up being this teeny tiny little sliver. And that is it. That is your area right there. Oh my goodness, that's so skinny. It's unbelievable. So that's how you do that. So now this intersection point is at the point 1, 1, and then the other intersection point is 0, 0. So that's good to know. And actually evaluating the integral is easy, because the innermost integral, when you're integrating just 1 with respect to x, you're just going to get x, and then evaluate x at the limits. So then you're going to get the cube root of y minus y squared dy. And cube root of y is the same as y to the 1/3, of course. And so you'll use your power rule, and you'll have 3/4 y to the 4/3 minus y cubed over 3. And you'll evaluate this between 0 and 1, and you'll get 3/4 minus 1/3 minus 0, and this ends up being 5/12. And that is the area. Any questions so far? Everybody got that, I hope? Now the hard part. How do you switch the order? So one thing you will know is that the dx dy has to be dy dx. That's a given. Now, do you just swap the two integral symbols too? Oh, no, you don't do that. That's not going to work. It won't even get you close. So don't try it. Because for one thing, you'll be violating one of the key rules of iterated integrals. And that is this outermost integral is only allowed to have pure numbers as limits. That's one of the big rules. In fact, let's use that rule and help us put the limits on the outermost integral. So since we're integrating with respect to x for the outermost integral, what limits should we be putting on there? Look at your region, this cute little sliver, and look at what the lowest that x hits and the highest value that x hits on that region. And I hope you can tell it's pretty easy. It's just going to go from 0 to 1. And those are indeed the limits for x. So we're good to go there. Now the hard part, what's y doing? Please don't say 0 to 1. You're going to be totally wrong. It's not even close. Well, it looks like on that region that y hits, you know, if you look at the lowest that y hits and the highest that y hits, it also goes from 0 to 1. Remember, the only time that all your limits are pure numbers, if all the limits were pure numbers, is for rectangular regions only. And I hope you will agree with me that this little sliver don't look like a rectangle. So don't even think about putting pure numbers only for the limits for y. So here's what you're going to need to do. What I'm going to do is I'm going to blow up the region just to make it more of a visual here. Here's my region, okay, when I blow it up. And since dy dx is the vertically simple region's choice, when I draw a little man inside my region, I'll draw him vertically. Now, I know you may think it's silly to draw this little man, but it just helps. So I notice the little man's head is on the upper curve, so it's going to be a variable limit. And his feet are also on something variable, that lower limit. Now, this upper limit was part of the x equals y squared graph, and the lower limit was the y equals x cubed graph. Now, here's, remember one of the rules for iterating your integral, you cannot have your limits match the variable of integration. So the lower limit here, it is legal. You want to put x cubed there. That's good. Here's what you don't want to do. So don't write this down, folks. Do not put y squared here. That would be bad. No, 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 no. Well, why not? Well, even though this graph has the equation x equals y squared, you need to rewrite it so that it's written as a function of x. So you'll want to square both sides, square root both sides rather, and don't forget your plus or minus, and solve it for y. So when I solve it for y, though, I get two answers. I get plus square root of x or negative square root of x. Which one should I choose? And it does matter. It depends on your region. In this case, this upper portion here is the plus square root of x. So, because it's above the x-axis. So that upper limit is going to be square root of x, okay? Or x to the half, your choice. Now you're done switching the order of integration. Yay! And now go evaluate it. We better get 5/12, otherwise we screwed up. So I'm going to do the innermost integral first with respect to y, and that's just going to be y going from x cubed to square root of x. And then do the fundamental theorem of calculus, plug in the upper limit first, minus, then plug in the lower limit. And then this is just an easy peasy calc 1 problem. And the antiderivative of x to the half, I believe, is 2/3 x to the 3/2 minus, and then the antiderivative of x cubed is x to the 4th over 4. When you evaluate between 0 and 1, yay, you are going to get 5/12. It works out, okay? So any questions on this problem? So that's your first foray into switching the order. It's not super easy. It's a skill, and you'll get better with practice, I promise. Okay, but give yourself some time to get better. So now let's discuss average value. What is average value? It's the average that a function takes on whatever you're integrating over. So let's do a review. In Calculus 1, you learn that the average value f over some interval. So I'm just going to give you a little picture here. Let's say here's your graph of your function f, y equals f of x. And let's say over this region a to b, you want the average value that f of x takes on. So you're not really being asked to find an area. You're asked to find average value of the function. But the formula for average value from Calc 1 looks like this. F, and it depends on your textbook that you use for notation. In statistics, they usually put a bar over a variable that they're taking an average of. I'm not making this up. If you haven't taken statistics yet, take it. It's a great class, Math 119. F bar, that means F average. Or some textbooks don't use that. They use subscript notation, AV, average. And so the average value is what you kind of do is you sum up all of the function's values over that interval, in this case interval, because you're integrating over an interval, and then you divide out by the length of the interval. And that is the Calculus 1 review formula. And the reason why I want to show you that first is there's an analogous average value here for the average that a function of two variables is going to take on a region of integration. So the average value of f, where f looks like z equals f of xy, is going to be defined as the following. F bar, that means f average, or if you prefer the notation f average, is equal to 1 divided by the area of the region R, that's your region of integration, multiplied by the double integral of that function of two variables. And now I'm going to introduce some weird notation that you need to start getting comfortable with. Instead of dy dx here, I'm going to put dA, where just a side note here, dA stands for either dy dx or dx dy. It's the area down there in the xy plane. And then instead of iterating this integral, I'll put a big fat R underneath the two integral symbols. That means you're integrating over the region. So if I show you a picture of what we're finding, the graph of z equals f of xy is some, surface. So I'll just do like a capping surface for now. Here's like a nice capping surface. There's the graph of the surface given by z equals f of xy. And it's hovering over some region down here in the xy plane that you're integrating over. You're integrating over that region here in the xy plane. So what you're finding here is the average altitude, if you will, the average z coordinate that's getting hit over this region R. And the way you do it is with this formula. So let's do an example, and then you'll get a chance to do examples in homework and have it on the quiz. Okay. Find the average value of this function, 4 minus x minus y. And by the way, this is a plane. Well, how do I know? Because it's linear. If I did have to graph it, I would replace the fxy with z, and I could rewrite it where I add x and y to both sides. And I hope you can appreciate that this plane, x plus y plus z equals 4, you should all remember how to graph a plane. You know, just graphing the portion of the plane here in the first octant, it looks like that. So that's the graph of the surface. Now we're integrating it over the region R. So we're not integrating over this whole triangle down here in the XY plane. That's not the region of integration. The region of integration we're integrating over is a little rectangular area where x goes between 0 and 2 and y goes between 0 and 3. So it's this rectangle down here that's our R. So we're trying to figure out the portion of the plane that's hovering above that rectangular region. So I'm trying to graph just the portion of the, I'll use a different color because this is getting a little bit messy. This portion of the plane only that's hovering over that region R in the XY plane, that's the blue rectangle. That's what we're trying to find, that average Z coordinate that's getting hit. Okay? That's average value, people. Oh, yeah. So our average value is going to be 1 over the area of that region times the double integral of the function 4 minus x minus y. So you put that there. And then I'm going to choose my order of integration dy dx, but it doesn't really matter because if you look at what's going on in the xy plane here, the x, they even told us, is going from 0 to 2. And y is going from 0 to 3. There's your region R. Heck, you know, so it's easy to iterate, put the limits on your double integral. X, they told us, it's going from 0 to 2. Boom, there you go. Y is going from 0 to 3. Boom, there you go. Area of a region, oh my God, this is too easy. This is the area of a rectangle. And for us, length times width is just 2 times 3, which is 6. So we don't have to do a lot of work to find the area of that region. Okay, so now so far we have 1/6, and then here's our iterated integral, and this is going to give us the answer, the average value of this function. So let's just quickly do this. I'm going to integrate with respect to y first, and this is pretty easy because integrating a polynomial doesn't require any u sub or anything like that. So I'm going to get 4y minus xy minus y squared over 2. And I'll evaluate this antiderivative between 0 and 3. And so I'll end up getting 4 times 3 minus x times 3 minus 3 squared over 2. And when I plug in the 0, everything goes to 0. So I'll just put a big fat 0 there. And now this is just turned into a single integral, which is just a Calc 1 problem. 12 minus 3x minus, 9/2, yucky. Let's see, 12 minus 9/2, I believe, is going to be 15/2. And so I'm really integrating 15/2 minus 3x, and then that's going to give me, is that right? 12, yeah. So I'm going to have 15/2 x minus 3/2 x squared. And then evaluate that between 0 and 2. And I'm just going to, you can do, I'm sure, the arithmetic. And I end up getting 3/2. And that's the average value of z equals f of xy over the rectangular region. Okay? So now you have another application for double integrals. One is to find the area of a region, but another is to find the average value of a function. And there's plenty more coming. Don't worry. Okay, So now let's do improper iterated integrals. So when you took calculus 2, you learned about something called an improper integral. And there were a couple types. The type that we're going to look at, although we could look at the other type too, but I'll save that for some other because weird things happen. But notice how the limit on one of these integrals is infinity. If even one of the limits is infinity or negative infinity or both, that's called an improper integral. So how do you do double improper integrals? Well, I teach it the same way I teach regular single integrals that are improper. And I don't replace the infinity with a letter and take the limit. I kind of do it a little bit more shortcutty. If you want to do it that way, that's fine, but you don't have to. So here we're going to do this double integral right now. It's an improper integral, and we're going to use some of our limit facts. So is this going to be on the quiz? Yes. Is it going to be on the midterm? Yes. Is it going to be on the final? Yes. What I love about improper integrals is it combines your knowledge of integration with limits all in one nice package. And I love that kind of stuff. I love those double whammies. So I love putting those on exams. And if you're like, well, you know, what's the application? There's a lot of applications. One of the applications is probability, which we don't have time to do, but there may be some homework in your textbook you can look at. So it's pretty cool. So if you take an upper division math class called probability theory, you will be doing double integrals and you'll be doing improper double integrals. So it's relevant. All right, here we go. How you do this? Carefully. First, we're going to integrate with respect to y. What does that mean? Well, x is held constant, so x squared is just a constant. So if it helps, you can kind of put the x squared over to the side as a multiple and then worry about integrating 1 over 1 plus y squared with respect to y. And this is the Arctan rule. I hope you can appreciate Arctan rule. And the u is y, du is dy, and a is 1. It's kind of easy. And so the antiderivative of this is going to be the x squared. That doesn't go away. And then you'll have arctan. I'll write it as tan inverse because my math lab tends to do that, of y. And you're going to evaluate this between his limits. Well, the limits were 0 to infinity. So now you have to use your limit fact. So I'm going to first substitute in the upper limit of infinity. Oops. Minus, and then substitute in the lower limit of 0. And does anybody remember what the arctan of infinity was?
I have.
Over 2.
Pi
Yeah.
over 2.
Yeah, good. How about arctan of 0?
So 1.
0.
0. Yeah, it's not 1. Arctan of 1, though, is equal to pi 4. So you should memorize that for the future. But this is pi halves minus 0, which is just pi halves. Easy peasy. And now we are just looking at a Calc 1 easy peasy integral. I'll pull the pi halves out because it's just a multiple. And then we go ahead and integrate this. Okay, x cubed over 3. And evaluate that between 0 and 3. And I get 3 cubed over 3, 27 thirds. I think that reduces to 9. Final answer, 9 pi halves. So what can we say about that improper integral? It converges. Do they all converge? No. You might get an improper integral that blows up, goes to infinity. Okay, to finish out my coverage of 16.1, although, yeah, they do a little bit differently in Briggs. I have a couple more problems here, and then we'll hit the next section. So I love this example 9 because it's sort of a double whammy as far as juiciness, juicy concepts. So before I do example 9 for you, I want to talk about certain kinds of integrands for double integrals. So here's a handy fact that I'll allow you to use anytime it's applicable. Now be careful because it may not be applicable. If you have a double integral that you're working on and it turns out that the integrand is so special, not all of them are this special though, where you can rewrite it as something that only has x's in it, so I'll just say f of x, times, not plus, times some other junk that has only y's in it. If you can do this, you are allowed to split the double integral into the product of two single integrals. So if this is true, then you're allowed to rewrite it like this. Oh, I'll just integrate the f of x junk with respect to x, and I'll multiply that with the integral of the other junk that has to do with y. Now, this can only happen if your integrand can be written as a product with a function of x times a function of y. Otherwise, don't even think about it. Like, don't be doing illegal math and doing some weird separations that aren't even legit, okay? I will not accept it, 0 credit, all right? So this is a nice little handy fact that I'll allow you to take advantage anytime it's applicable. So is it applicable here? Because it kind of doesn't look like it. Well, here's a little bit of scratch work for you. E to the negative quantity 2x plus y squared can be written as e to the 2x, negative 2x rather, times e to the negative y squared after I distribute my negative, of course. And then I'm using an exponential rule. So do you agree with this, that it's true?
Yes.
Yeah.
If you do, then I hope you can see that this integrand, I can rewrite it as x e to the negative 2x times y e to the negative y squared, like that. Ooh-hoo, ooh-hoo.
Actually, I think we
Yay-hoo, yay-hoo. That's an awesome thing. Now it makes it a little bit easier to integrate. Now, what if you didn't notice this? Could you still integrate it? Absolutely. It's a little bit messier because your x's and y's are all interleaved, but you'll just go for it. So if you don't do this, you still can do it. Well, how? You would use the exponential rule, e to the u du, to start. Okay. Now, since I rewrote this as a product of a function of x here multiplied by a function of y, I am going to split it up into two separate integrals and take the product of those guys because I'm allowed to. You know, if I can make things a little easier on myself, I will. Okay. So now let's do each of these separately and then we'll multiply the results. So let's work on the first factor here. Bad news, this one you don't do with the exponential rule. You need IBP, integration by parts. Well, you're going to let u be x, dv be the remainder of the integrand, e to the negative 2x dx, and then the du will be 1 dx, and the v will be the antiderivative of e to the negative 2x, which is negative a half e to the negative 2x. And then when you do your integration by parts, which is uv minus the integral of v du, don't forget, you'll get x times negative a half e to the negative 2x minus v du. I'll have negative a half e to the negative 2x dx. Okay, what a mess. And I'm purposely not evaluating at the limits yet. I usually like to find my antiderivative completely when I'm using integration by parts, then I evaluate it at the limits. So this minus and this minus can combine. And these two guys, I'll rewrite it a little bit cleaner where the coefficient is in front. And I appreciate if you would do that also anytime you are writing out nice factors. And then this, we already integrated that. That was negative a half e to the negative 2x. And then now you're ready. Well, I'll just clean this up a little bit. What the heck? This is going to be minus a fourth e to the negative 2x. Okay, now you're ready to evaluate at the limits, 0 to infinity. And be careful because a lot of times when we look at the 0, because we're always in a hurry, we go, oh, the 0, everybody's going to go to the 0. That occurs if you're maybe looking at your antiderivative being a polynomial, but if you've got exponentials in there, don't do that, or cosines or something like that. So when you plug in the infinity, though, let's just do the direct sub. And then when I plug in the 0, okay, now this is not 0. This is going to be minus a fourth. This is a 0, 0 times anything is 0. When I distribute the negative, I'm going to end up with plus 1/4 there. And then I use my limit facts. E to the negative infinity goes to 0. But this is an indeterminate. This is infinity times 0. And this is indeterminate. So you can't say what that is. Be careful. Don't go infinity times 0 equals 0, because that's not true. So let's do a little bit of scratch work over here on the side. X e to the minus 2x, when you take the limit as x goes to infinity, you get infinity times 0, which is indeterminate. You learned this from Calc 1. Maybe you forgot. I'm here to remind you. Then what? Well, what they taught you in Calc 2 was you try to rewrite the expression as a quotient so you can use L'Hopital's rule or growth rates. And so here, when you now use direct sub, because e to the negative 2x can be rewritten as 1 over e to the 2x, this is looking like infinity over infinity, which is also indeterminate. But at least you can now use L'Hopital's. So LH, that's L'Hopital's. So you're still going to take a limit as x goes to infinity, and the derivative of x is 1, and the derivative of e to the 2x is 2e to the 2x. And now when I use direct sub, I get 1 over infinity. But that's 0. Oh, okay. We're done with the scratch. What can I say? This thing does, in fact, go to 0. And so my result for that first integral is 1/4. Save that for later. Save it for later. You're not done. What do you mean? Well, remember, we're in the middle of doing a double integral. And so the other factor was this integral right here. We still need to take care of that guy. So let's do that guy right now. So you're integrating y e to the negative y squared dy. Now this is the exponential rule. So go ahead and tell me the u and the du to get full credit on my quizzes and exams, please. That would be great. And the du is y dy, but we need a -2, provided we divide 1 out. And once we do, when we rewrite it using u's, we get that. And then using the exponential rule and replacing my u with -y squared, and then we evaluate this between the limits, 0 to infinity. First, I'll plug in the infinity using direct sub, and then I'll plug in the 0. E to the negative infinity goes to 0. Minus minus is a plus. E to the 0 is 1. I get a half. Final answer, you take the first integral's result, which I believe was 1/4, right? And you multiply it by a half, and your final answer is 1/8. So the improper integral converges. Yay! And we all go home happy. So the beauty of this problem, this improper integral problem, was we were able to use that handy fact of rewriting the integrand as a product of a function of x, a function of y. So you don't always get to do that, but if you can, it's nice. So now we're going to do one where that's not the case and you're stuck. You have to think a little bit. So I like to do example 10 because you're going to see a lot of homeworks that have this flavor, this idea that I'm about to go over. I haven't done an integral this hard yet. So pay attention because it's weird. This isn't this kind of stuff you do in a Calc 1 class because it would be illegal. You'll see in a moment. In Calc 1, if you're missing a variable, that you're not allowed to put one in. You're allowed to put a multiple in, but not a variable. But if your variable of integration is different from the variable that you need, and the variable that you're treating as a constant, you can. So it's kind of cool. That's what's kind of fun about double integrals. So check this result out here. You're integrating e raised to the x divided by y squared power. Ugh, what the heck? That looks kind of funky. I know. No worries. We're going to integrate it with respect to x. Okay, that means we're holding y constant. Yes, that's right. And so we're going to use the exponential rule. So the u will be x over y squared. And then du, and remember the du, we're doing an integral with respect to x. When you differentiate x over y squared with respect to x, you get 1 over y squared dx. but I don't see a 1 over y squared hanging around in the integrand, and I need it. Otherwise, I can't move forward. So how am I can I, even though that's a variable, can I stick a 1 over y squared in the integrand? Sure, provided you multiply on the front of the integral by its reciprocal, which would make it all legal. That would basically be multiplying by a special version of 1. So that's the trick right there, people. So what am I saying? This integral will still have the outermost integral. You're going to put in a 1 over y squared in the integrand because you need it to be your du, so long as you multiply the front of it by y squared, because that's really just multiplying by a special version 1. Now this inner integral looks like the integral of e to the u du, and the result is just e to the u, which for us is e to the x over y squared. And we'll evaluate that between the limits of 0 to y squared. And it looks like I'm running out of room, so I'm going to need to come down here and finish it up. Yikes. So what do I have here? I still have the outermost integral, and then I have my e to the u, and I'm evaluating it between the limits. So I plug in the upper limit first, and then I plug in my lower limit. That's a 0 right there. And the y squared over y squared, that just reduces to 1. And e to the 0 is just 1. So folks, this is just some number here, some weird number, e minus 1, okay? Because it's a multiple, I'm allowed to pull it out in front of the integral. And now I'm just integrating 1 with respect to y. Oops, sorry, I'm trying to write way too fast. And I've got the weird number, e minus 1. Was that a y or a y squared? I screw up there. Oh, I forgot my y squared. Sorry. I'm trying to do this down here. This y squared is still there. I forgot him. Sorry, guys. Y squared. He's still sitting in there. Sitting in there. So you're really integrating y squared. And so his antiderivative is y cubed over 3. And then you're evaluating him between the limits. So this is just going to be some weird number. Very weird number. Sometimes you get weird numbers. Oof. Okay. E minus 1 times 7/3. Okay. That's my weird number, and that's the weird final answer of this double integral. So what was the moral of the story? The moral of the story is when you're doing these multiple integrals and you're using u sub, when you're treating your variable of integration and the other variables are constant, you're allowed to put in constants, which might involve variables. So that's kind of fun. You'll see that more than once. Will that be on my quizzes and exams? Absolutely. Okay, I'm done with the what I consider 16.1.
That blank spot on example 10 would be multiplied by conjugate or special value 1.
Let's see, the blank spot provided that, no, not a conjugate. I'm sorry. I would put in the blank would be, this will be okay, provided that it's considered a constant with respect, W period, R period, T period, with respect to the variable of integration. My Microsoft Surface Pro is now dying. Oh, I see why. Okay, hang on a second. Power problem. Okay, we're better now. Looks like my cooling stand is dead. I have to have a cooling stand for this Microsoft Surface because it runs hot. My cooling stand is unhappy here. Why, cooling stand? He's not getting it's not getting power. Okay. All right. So let's do double integrals in volume. So we're moving on. So in the next section, they talk about another application of double integrals, which is really fun. big time application. And yes, this is going to be on your quiz. So a really cool application for double integrals is finding volume. Oh, first a mean. Okay. Okay, I'm going to do the hand waving derivation for this on why it works. And folks, this is analogous to using a single integral to find area under a curve. So I hope you recall when you were in Calc 1, what they probably did, this is just to sort of remind you of what we're about to do, is when they first were going to teach you about an integral, and you were just a babe in the woods there in your Calculus 1 class. And they go, hey guys, we're going to look at finding the area underneath the curve. And you're like, yeah, so what? And they said, what we're going to do is we're going to subdivide the interval going from A to B into some equal subintervals like this. And then we're going to create these cute little rectangles, one for each subinterval. Do you remember this happening, people?
Yes.
Remember this? And they go, since we know how to find the area of a rectangle, we'll just find the area of the ith rectangle, which is fx sub I, that's the height, times the width, delta x sub I. Remember this? And then we'll sum up all of the n rectangles. And this is known as a Riemann sum. And then they tightened up the partition and, you know, made skinnier rectangles and took a limit as the norm of the partition goes to 0. And then they ended up with an integral. We're going to do a similar thing right now. We're going to come up with a Riemann sum here in Calc 3. So how does that work? Well, what we're going to look at here is a surface, and you can kind of look at this surface here. It's like a capping surface. And it's hovering over some region here in the XY plane. Fine. And we're going to find the volume of that solid, essentially. That's got, you know, the base of the solid is this green thing down here in the XY plane, which I just shaded red. That's the base of your solid. And the cap of the solid is given by the surface, function of two variables. Cool. So how do you do that? And we are going to make sure for now that our function is positive, which means it's always above the XY plane. But later on, we'll relax it. But if you're going to find volumes of solids, you need this to be true. Otherwise, you'll get negative volumes. We want to kind of avoid that. But you guys got negative areas when you relax the standard of having the function up here no longer having to be positive. So we'll do the same, but not yet. Okay, so what they do is they do a partition, but instead of partitioning the interval, we partition the region, the base of the solid, and they do it by superimposing this rectangular grid over the region, as I have in the figure. And then the rectangles that you have there all lie inside that region, and they form what's known as an inner partition. They call the inner partition delta. The norm of the partition, which kind of looks like a magnitude, you can kind of think of it that it is the length of the longest diagonal of all the n rectangles. In other words, the rectangles may or may not be equal in dimension. Okay, and then you pick an arbitrary point, x sub I, y sub I, in the ith rectangle, like down here. And then you form a rectangular prism, this rectangular prism, whose height is given by f evaluated at x sub I, y sub I. That's a z coordinate, essentially. That's your height. And then they give you the volume of that little rectangular box, the volume of that rectangular prism. And it's basically length times width times height, where the base down here, you can think of that as width times length, and then this is the height, if you will. So here's your h, your height, and your width times your length, they're just calling delta a sub I, the area of the base. Okay, that's it. And they form the Riemann sum because you're going to have n of these cute little prisms. There you go. And that looks like it's going to be a pretty darn good approximation of the actual volume of the solid, give or take. Okay. And then the claim is if you tighten up your mesh of your grid to form smaller and smaller rectangles down there, smaller and smaller bases of the prisms, you can take the limit of as the norm of the partition goes to 0. So you're taking the limit of your Riemann sum. Okay, yeah, so now what? Well, it turns into a double integral. Well, how come in Calc 1 it turned into a single integral? Because this delta A sub I turns into delta X sub I, there's your width, times delta Y sub I, there's your length. And so you have two variables to do business with. So what that means is when you take the limit, you're going to end up with a double integral. Okay, so there's your definition of a double integral, people, is it's the limit of a Riemann sum. Great, provided the limit exists. And if the limit exists, we say that the function f is integrable over the region R. Fine. Now, if you put a few more sufficient conditions, now I updated this over the weekend, so you have a blank here, but if you want to try to write down this really fast, I decided to just put it here quickly so you don't have to write so much. But the conditions that you're restricted to, if you're going to use this as a volume, the R has to be able to be written as a sum of finite, non-overlapping regions, subregions that are either vertically or horizontally simple, and you need the function to be continuous on R. Otherwise, you know, that double integral won't exist and you'll be screwed. You'll get something weird. Okay, if you have those conditions being met, everything's happy. It is possible to use the double integral as representing the volume of a solid. And there's other representations though. Please don't get addicted to this one thing. Don't come to me, you know, in 2-3 weeks after we're done with this module and go, hey, I thought we're only allowed to use double integrals for volumes. No, there's lots of things you can use double integrals for. It's one cool application of a double integral. There's more. So the volume, if you've got f integrable over your plane region R and f is above the xy plane, so f is positive, it's above, the capping surface is above the xy plane, then you can do the double integral as a volume. So your volume will be double over the region R, and you simply put your capping surface as your integrand. That's the key right there, people. When you're going to do the volume of a solid and you're given the capping surface goes into the integrand. Boom. Okay. So don't come up to me and go, hey, how do we do the volume of a solid? I don't remember. Capping surface goes as the integrand. Well, what about the limits? What about your region? That's going to be the hard part. Yeah, that's where you got to practice. Okay, got to do Fubini's theorem first, then we'll do a whole bunch of examples. Here we go. And I've got to hurry. I don't have much time here. I'm going to really have to hurry. Okay. All right, well, we might go a little bit late. So Fubini says if you have x going from a pure number to a pure number and y going from some variable function to some other variable function, then when you're trying to use your double integral as a volume situation, choose dy dx as your order of integration, because it'll be obvious, because the outer integral is with respect to x and they gave you the pure numbers, and then the variable limits are for y. On the other hand, if they define your R where y is going from a pure number to a pure number and x is variable, then you'll want to iterate your double integral. Iterate means put the limits on, where the order of integration is dx dy. Your capping surface is still going to be the integrand, but your order of integration will be dx dy, and then your x limits go here. Okay, and there you go. That's Fubini. Now let's do a whole bunch of examples. Okay, so your first example here, it looks like it got kind of cut off. We're finding the volume of a solid bounded by this plane, x plus 2y plus z equals 2, and by the 3 coordinate planes. What does this mean? It means you're in the first octant. What is the first octant? So this solid is in the first octant. What's the first octant? It's where x, y, and z are all positive. So in the x, y, z coordinate system here, it's like the area that's coming out at you. So if you graphed this plane, and you guys all know how to sketch graphs of planes, you'll be able to notice that the x-intercept is 2, the z-intercept is 2, it looks like the y-intercept is 1/2. And you're finding the solid bounded above by that ceiling, and the base of the solid is in the xy plane, and the base of the solid is this triangular region here. So how do you set up the volume representing this solid? Well, you go volume equals double double. You first solve for z, because you need z equals fxy to be your integrand. So when I solve for z, I get 2 minus x minus 2y. That goes down here into the integrand. And then you get to choose your order of integration. But before you do, go look at the base of your solid, because that'll kind of help you decide if it's vertically or horizontally simple. And sometimes it's both. You can just choose whichever is your favorite. If you graph the base of the solid, the quick and dirty way, since this capping surface cuts through the xy plane, the trace right there is given. If you set z equal to 0 in this plane equation, and you'll get x plus 2y equals 2, that's the trace of the capping surface as it cuts through the xy plane. Now, folks, your capping surface won't always cut through your xy plane, so you may not get this lucky. But here it does, and it helps us see what the base of the solid is. So now what? Looking at the base of this solid, you can use either dy dx or dx dy, whichever is your personal favorite. My personal favorite, and I bet yours is too, is dy dx, because I prefer functions of x rather than functions of y. That's just how my brain thinks. So it's easier to think of for most people. So now the outermost integral is going to go from a pure number to a pure number. And if you look at this cute little base of the solid, it should be obvious that x is going from 0 to 2. Now, please do not say that y is going from 0 to 1, because that is false. Well, it looks like it. There it is. Remember, if all 4 of those limits are pure numbers, that means the region of integration would be a rectangle, and this is a triangle. This ain't no rectangle. So you're going to put a little man in there to help you decide the limits for y. Now, the feet of the little man are flat and firmly implanted on the x-axis, which is good news. So no matter where you move the little man, where I move him to the left or right, because where you put him is arbitrary, his feet will still be on the equation of the graph of y equals 0. His head is variable, though. He can get shorter or taller based on where you place him. And so you're going to have to solve this equation for y, and the upper limit is 2 minus x over 2, that diagonal line. And now you just set up a double integral representing volume. Congratulations. So now if I do this problem, and I'm going to go very quickly now, I get 2y minus xy minus y squared over 2. And I have these limits, which are pretty nasty. And so you're probably going to get really depressed, but I'll give you a little tip that I'll allow you to do. And if you plug in 0, everything goes to 0. Now, do you see this is a little messy? There actually is a trick I can do here with some factoring and clean this up. But when you're doing a quiz or an exam in my class, and you get to the point where you have like a polynomial that's going to, if you did have to, you're going to have to multiply this out, and unless you can do that factoring trick, it's going to be a little bit time consuming. So at this point, you can't do this for like sine or cosine or exponentials. I don't want you to do that. For nasty polynomials here, use your graphing calculator and use the function integrate menu selection there, and it should come out nice, because this is just a single integral. And if you do that, you should get 2/3 as your final result, 2/3 units cubed, because this is a volume. Yeah. And you're representing, you don't know what the units are. It could be meters cubed, feet cubed, who knows? And we're done with that problem. So to recap, we're finding the volume of a solid using a double integral. Let's do another one. This one's a little bit weird, but not too weird. They're giving you a capping surface. And if I draw that, and you can also graph this, and I'm kind of short on time, but I claim that that is a paraboloid, that capping surface. In fact, it's a paraboloid opening upward with its vertex there at the 1 on the z-axis. Okay. And then this is, oh dear, what the heck is that? Well, that's a plane. And by the way, anytime you see bounded by the 3 coordinate planes, that's going to automatically mean your first octant. So it's coming out at you where X, Y, and Z are all positive in that first octant. So the capping surface, this is the ceiling. This is the ceiling of some solid. It's a weird ceiling because it's like one of those vaulted ceilings. So what are you going to do? Well, what I would do is I would graph this in the XY plane. So if I rewrite it as y equals 2 minus 2x, I'll get that line. And since they told me it's bounded by the 3 coordinate planes, that automatically means that it's bounded by the X and Y axes, and we're in the first quadrant for the base of the solid. So I claim that the base of the solid is given by this little triangular sliver in the XY plane. So down here, I know it seems kind of weird, is the base of your solid. So what does the solid look like? This is getting awfully hard to picture, and you don't have to picture these solids, but what I want you to get is the base of your solid is here in the XY plane, and the capping of it is this curvy thing. So it's kind of a weird looking solid that you're trying to find the volume of. It's got a curvy top. Kind of weird looking, isn't it? Go find the volume of that weird thing. So you're going to go volume equals double over the region R. This is your region R, the base of your solid. And you put your capping surface as your integrand, and then dA. dA is sort of generic. You got to go pick your order of integration. And as usual, I prefer my order of integration to be dy dx. Okay? So I didn't draw this over here, but I guess I could have. There's my region R. Okay? Now, X looks like it's going from 0 to 1. But if I put my little man in there in my vertically simple region like this, it looks like his feet are again on the x-axis, so the lower limit is 0, and his head is on the diagonal line, which has the equation or the graph 2 minus 2x. And then this is the volume right here, represented by that double integral. And again, you're going to run into that weird thing where after you integrate with respect to y, and you evaluate this antiderivative between the limits, it's going to look terrible. Like, unless you like foiling and all that stuff, which you can. I used to make my students do this by hand, face to face, but I think I'll just say, you know what? I know you passed Calc 1. You're graduates of Calc 1. Go use your graphing calculator at this point using the FNINT command. And you should, et cetera here. And you'll get 11.6 cubic units, of course. That's the volume of that weird looking solid. Okay, now we're going to do something hard. What? Yeah, in the last 10 minutes of sort of class, we're going to finally hit it, and it's going to be hard. What? Yeah, and I may skip example 13. You don't need example 13. I mean, not 13, but 14. Sorry, my notes. So we'll for sure do 2 more examples, and then I'll set you free, okay? And you'll have enough tools to complete on your quiz 7. In excellence. And I do have office hours today. You're welcome to come. Noon to 2. See you there. Otherwise, have a good weekend. So I heard you like integration, you dog. So we put an integral in an integral so you can integrate while you integrate. And that's basically what a double integral is. It's an integral inside of an integral. And if you're a computer science person, it's kind of like putting a loop inside of a loop. We do nested loops all the time in comp sci, don't we, folks? If you're a comp sci person, you know what I'm talking about. Yeah. Okay. So now let's do a problem that is going to be similar to what's going to be on the quiz and the midterm and the final. There's going to be 1 on the final, at least 1 on your midterm 3, probably 1 on midterm 4. and definitely one on the quiz this weekend. So what is it? Well, it's going to be a problem, and you've seen it before, where there's no way to integrate unless you switch the order of integration. Ha ha! You have to know how to switch order of integration. It's going to save you. Okay, so what do I mean? They want us to consider a solid region in the first octant again. Are all the regions going to be in the first octant? No. In fact, my last example is not. So I don't want you to get addicted to everything we do in the rest of the semester is in the first octant. I have students who think like that, and then I purposely always put at least one problem on a quiz or exam that isn't restricted to the first octant, and then they choke. So be careful. So the capping surface is given by e to the minus y squared, fine. And it's the region is also bounded by these planes, x equals 0, y equals 2x, and y equals 2. Those are planes. I mean, you can think of y equals 2 as being a horizontal line, but if you graph y equals 2 in the world of 3D, folks, I want you to get, in the world of 3D, it's a plane that's vertically sitting there intersecting the y-axis at the 2. So this solid is going to have different sides to it. But more importantly, you want to graph these traces of these planes in the xy plane, because it's going to give you access to what the base of the solid looks like. And if you don't know what the base of your solid looks like, or you'll see later the projection of the solid onto the xy plane, you won't be able to set up your double integral. So sometimes, even though they don't ask me to sketch my base of my solid, I do it anyways. And on this weekend's quiz, you're going to see, I'm going to put as an instructor tip, in order to receive full credit, even though my math lab may not ask you, you got to sketch your region of integration, because if you don't, you won't get your full points. And you'll thank me later because it helps anyways. So if you graph all these, like x equals 0, okay, that's a vertical line on top of the y-axis, fine. Y equals 2, that's easy, that's a horizontal line, fine. Y equals 2x, okay, that looks like a diagonal line like this. My region of integration, the base of my solid, basically, this is R, and it's the base of your solid. Looks like that. That's the base of my solid. Now, just for kicks and giggles, I'd like you to see what the capping surface looks like. I mean, obviously you don't have to, because you guys may not want to go into GeoGebra and go do the fun and games. But if I graph fxy, replace it with z, e to the negative y squared, and check that baby out. Woo, that is pretty, isn't it? Oh my goodness, that looks, stop spinning, you're making me seasick here. So that's kind of nice. That's what the capping surface looks like for this lovely solid. It's that curvy looking thing, and I like always doing with my colors. So that's kind of pretty. That's a nice capping surface. I like it. And if you can imagine, the portion of this capping surface that's hovering over that triangular region in the xy plane would be what our solid is looking like. Okay, it's got that curvy top. Kind of pretty. Okay, so back to hand-to-hand combat. So if I accidentally start setting up my volume, it's not really an accident. Like you might go, hey, I like dy dx. That's my favorite order of integration. Okay, and it looks like x is going from 0 to 1. And be careful, what's y doing? If I put my little man in there, because dy dx is the vertically simple choice of order of integration, like that, there's my little man. His head, no matter where I place him arbitrarily, is always going to be on that upper limit of y equals 2. That's a constant. But his feet look like they're going to be variable. His feet are on that diagonal line, y equals 2x. So this is the double integral representing the volume. And it looks like nothing's wrong, doesn't it? But there is something wrong, and it's a big time wrong, because you can't integrate this. Yeah, this is not integrable. Well, look, try to integrate e to the net minus y squared with respect to y. It's not integrable. Oh, well, I'll use u sub. Good luck. Go try. You're going to run into a brick wall, and it won't be fun. So what are you going to do? You're going to switch the order of integration, because it's going to turn out, if you have dx dy instead, the e to the negative y squared capping surface will look like a constant with respect to x. And then we can always integrate constants. So that's why you want to know how to flip the integrals over. I mean, this is like cool. So what does that mean? So that means your volume is still going to be a double-double. And by the way, your capping surface doesn't change. I had one student like 6 years ago. She always like replaced in her capping surface X's with Y's and vice versa every time she switched her order. And I kept saying, what are you doing? No, the capping surface doesn't get swapped. You're confused. Please stop doing that, because I just would give her 0 points, 0 points every time until she finally stopped doing it. Oh, yeah. So the only thing that swaps, if you will, is the dy dx turns into dx dy. Okay, now what? Well, now let's do the outermost limits first, because those are always pure numbers. Great. So the pure numbers that y is doing, if you look at the y-axis, is 0 to 2. What's x doing? Now, since this is the horizontal order of integration choice, your horizontally simple region choice, your little man is going to, oh shoot, you're going to have to draw him in there horizontally. So you have to draw him sideways like this. Okay? And yes, it matters. And his head has to be pointed to the right. Don't blow this, because if you have him backwards, you're going to get a negative answer. And then when you give me a negative volume, I don't even look at your problem. I just take away all your points, because you should know better. So if you look at the little man's feet, no matter where you arbitrarily place your little man, his feet are always going to be solidly planted on that y-axis, which has the equation x equals 0. Oops, sorry, this is supposed to be 0 to 2x. So the lower limit for x is 0, but his head is variable. It's on this diagonal line, y equals 2x. But you don't want to put 2x as the upper limit, because remember, you're going to violate a rule. The rule that says the limits aren't supposed to match the variable of integration. So please don't do that. Instead, go on the side margin here with some scratch and solve the equation y equals 2x for x. And I get x equals y over 2. And y over 2 is what you need to use for your upper limit for the x. Now you're ready to rock and roll. Yeah! You can integrate e to the negative y squared with respect to x, because that just looks like some constant multiple. Oh man, that's awesome. And then what? Well, you still have to evaluate your x from the limits, and then that's just going to be y over 2. And I'm going to pull the half out just because it's bothering me, if you don't mind. And then when I look at this integral, this is totally doable, because this is the exponential rule, where u is negative y squared, du is negative 2y dy, and I just need to put a negative 2 in there, provided I multiply the front by negative 1/2, and now I have negative 1/4 e to the u du. This is what I was saying, you're not allowed to use your f and int at this point. I want to see you do these kind of things by hand, because this is, showing me you know how to integrate. And then you're going to evaluate this between 0 and 2, and you'll get a weird number. That's okay. So my final answer is negative 1/4 times the quantity e to the negative 4, e to the negative 4, minus 1. And I'm going to leave it. And I claim this is a positive answer. Well, it looks negative. Well, if you distribute the negative instead, you could rewrite it like this. Both of those are correct. And so this is a positive result. You can go check it on your calculator. I'll accept either one. And that's cubic units. Cubic units. That's the volume of that solid. So what was the moral of the story for that example? The moral of the story, there's a few morals of the story, but the key one is after you set up your double integral, you may find you have to switch the order of integration in order to even integrate it, okay? And that's fun. And then you know how to integrate using integration rules. Okay, so let's take a look at the last problem, and I just want to at least set it up. Example 15, because this is a solid that is not restricted to the first octant. So I don't want you to get addicted to everything's first octant only, because it may not be. So be very mindful when you're doing the problems. How do I know it's not? Well, because I don't see in the word problem here when they're saying consider the solid region bounded by these equations, it doesn't say first octant, so that's one possible. And it doesn't say bounded by the 3 coordinate planes. You see, if it's bounded by the 3 coordinate planes, that's another fancy schmancy way of telling you that you are indeed in the first octant. But they don't say that anywhere here. Now, that doesn't mean it won't be first octant only either. So you have to be careful. Don't go, oh, that definitely means it's not first octant. Not so fast, Kimosabi. So first up, it doesn't look like they gave me a capping surface. So this kind of problem is kind of confusing. And I purposely put this kind of problem on exams to see if students are really getting all this. And I claim the capping surface is given to you because it's secretly given to you with a z in there. So if you solve for z, this is your fxy, and this is your capping surface. And it's just a plane. Well, what's the base of the solid look like? And that's the hard part for this problem. What the heck is the base of the solid? So you're going to sketch the region of integration, which is basically what the base of your solid is going to be. Well, they did give you x minus y squared equals 0, which is actually a cylindrical surface. That's one of the walls of your solid. And if I asked you to graph x minus y squared as a cylindrical surface, the way you would do it is you would first draw the generating curve, which is x equals y squared, and then you would whoosh the x equals y squared along the z-axis parallel, and so it would look like that. That's one of the walls of this solid. Okay, it's kind of curvy. So, but it is cutting through the xy plane, so the trace that cylindrical surface is making in the xy plane is helping for the base of our solid. Okay. So what else? And I think what's missing here is, I think they should say excuse me, I should say, they should have something on here where z equals 0 also. Put that in there, because that means at least the base of the solid is in the xy plane. That's a typo. I'm going to have to fix that later. Otherwise, this could be a little bit tricky. And then now it looks like it's you have an infinity base. Like, does the base of your solid go on forever like this? No. This is the hard part. Because this plane, this capping surface does intersect the xy plane, where if you set z equal to 0, you'll get x equals 2. So x equals 2 is going to give you access here to the base of your solid. There it is. And it's not restricted to the first quadrant. Okay? So now get the volume. So I'll set it up and then I'll let you figure it out. I'll set it up 2 ways and I'll give you the answer. Okay. Because this x equals y squared is a function of y, the easier choice, if you're going to set up your double integral, would be dx dy. It's actually easier to set it up as the horizontally simple when you have functions of y. So why is that? Well, you got to figure out these intersection points. You know that x is 2. But if x is 2 and you solve for y, you'll get y equals plus or minus square root of 2. So you're going to get these 2 intersection points. So the pure numbers that y is ranging from is negative square root of 2 to positive square root of 2. Yeah, you can have weird limits. So what's x doing? Well, x is variable, and if you put your sideways horizontally positioned little man in there, like this, his head is on the upper limit, which is the equation x equals 2, and his feet are on the parabola, which has the equation x equals y squared. Okay? And if you do this whole problem, you should get 32 square root of 2/15 cubic units. What if you wanted to set this volume up using the dy dx instead, just because that's how you like to roll? Sometimes it's not doable, but this case it is doable, but it will involve most likely much more difficult integration. It might involve change of variables, but I'm just saying, but it can be done. Let's just do it. If you do this, the outer limit, it has to be pure numbers. So on this region, x is going from pure number 0 to pure number 2. Y, what's y doing? Well, this is your vertically simple order of integration. So you're going to put a vertical little man in there. And this is where it gets weird. The vertical little man's head is on the parabola and his feet are also on the parabola. But keep in mind the parabola is written as a function of y. So if you rewrite it by square rooting both sides, you'll get plus or minus the square root of x. And that'll work because the positive square root of x is where the little man's head is, and negative square root of x is where his feet are. And this should work, and it should get you the same number as an answer. Okay. Sorry I went over late. If you're still here, God bless. Sebastian, I talked to you real quick, and we'll stop the recording, and I'll see you guys